Welcome to the second lecture in Statistical Rethinking 2022. We have a lot of work to do today. We're going to start with some small problems in Bayesian inference, and then we'll use the same logic from these problems throughout the rest of the course. The first small problem is the Earth. When you consider the Earth from space, it is mostly water. 2/3 is covered in clouds on average, and about 70% of the surface is covered in water. How would you know that? Well, we know it because we have high quality maps, but you can also imagine a randomized Monte Carlo process to learn it. If you imagine all the space debris crashing into the Earth, little rocks, meteors all the time, about 70% of them land in water and about 30% on land. So if you could catalog those impacts, you would have a data set you could use to make inferences. We can't do that. We're not in orbit. We're not going to hurl rocks at the Earth and count the impacts. But we could take an inflatable globe and do this. When I've taught this course in person, this is exactly what I've done. I have an inflatable globe in my office that I use for this purpose. You can throw it into the audience, and then when a person catches it, they look where their right index finger is pointed, and if it's water, we record a water, and if it's land, we record a land. After a certain number of samples, we have a data set, and now the question is, what do we do with that data set? So let's imagine how that process looks. Here's a virtualized version of my inflatable globe. It's a geographically accurate, more or less, computer version of the globe, and we can spin it and take a random sample. First one is land, the second is water, third is land, fourth is land, fifth is water, sixth is also water, seventh is water, eighth is land, ninth is water, and the 10th is water. And we'll stop there. Now we have a little modest data set, 10 samples from our globe. These are random samples from the surface of the Earth. How should we use the sample to make an inference about the proportion of the Earth's surface that's covered in water? There are lots of ways you can use data to produce summaries, and we have to have an answer to this. Also, given a summary, how would you represent uncertainty? Obviously, more data is better. With only 5 samples from the globe, we would have less certainty than we do with our 10. And if we had 20 or 40 or 80 or 160, it would be even better. How should we represent that uncertainty? We're going to use Bayesian data analysis to answer all 3 of those questions at once. Bayesian data analysis is a very modest approach to inference, and it can be summed up with the words on this slide. For each possible explanation of the data, we're going to count all the ways the data could happen. And those explanations with more ways to produce the data are more plausible. Now I'm going to spend the rest of this lecture expanding on this and making it algorithmic so you can understand how it works. But you should know that every Bayesian model instantiates this approach. And this is how data are used to produce inferences, how they are summarized, and how uncertainty is represented is all through counting of ways that data can happen. Okay, so we're going to apply that logic to our proportion of the Earth that's covered in water problem. This is a bit too complicated a problem to start with, though, because there are an infinite number of explanations, because each proportion, whether it's 0.1 or 0.2 or 0.5, is a possible explanation of the data, as you'll see. And there are an infinite number of those proportions, right? Because there are an infinite number of real numbers between 0 and 1. So let's start with something a little easier, and where we can really just count a finite number of explanations, and then we'll loop back to the Earth problem. This particular picture of the Earth is a famous one. It's called the Blue Marble. It was a photograph that was taken from one of the Apollo missions, maybe Apollo 17 in the 1970s. Let's shrink this blue marble down, and we're going to think about marbles in a bag as an initial analogy for how we do inference in these settings. So now imagine there's a bag represented on this slide on the left, and it's going to contain 4 marbles. And some of them are blue, like the Earth, and some of them are white. And but there are only 4, and we take this as given information. But you don't know how many of the marbles are blue and how many are white. But with this information, we can enumerate all the possible explanations of any sample we get, and those explanations are just the contents of the bag. And there are 5 different possibilities shown here in the middle column. First, all of the marbles could be white. Second, 1 could be blue and 3 could be white. 2 could be blue and 2 could be white. 3 could be blue and 1 could be white. Or finally, all 4 of them can be blue. And we're going to assume that we've reached into the bag and sampled with replacement 3 marbles. So what that means to sample with replacement is after we draw out a marble, we put it back, we shake the bag, we draw another. We've done that 3 times, and we've observed in sequence blue, white, blue as our sample. And now the question is, given that observation, how can we use that to make an inference about which of the possible contents are most likely? And we're going to do it the Bayes way, just by taking each possible explanation and counting all the ways that the observations could arise given that assumption, given that explanation. So in this case, let's take the second one to start, the second possible set of contents, 1 blue marble and 3 white marbles, and we're going to assume the bag contains that for the moment. And that, by assume here, we just mean we're going to playfully assume that's the case, that that's the reality we're in, and we're going to deduce the consequences of that assumption. By assume, I don't mean we're going to assume it's true forever for now. This is a form of analysis. For the moment, we assume it's true. As you'll see, we'll do the same for all of the possible explanations. So how many ways are there to observe blue, white, blue if the bag contains 1 blue and 3 white marbles? We're going to use a device I call the garden of forking data. And in the garden of forking data, what we do is we draw out all the possible events that could happen from each sample. So imagine our first draw from the bag. This is our first possible observation. There are 4 things that could happen, assuming the bag contains 1 blue and 3 white marbles. So there, in a sense, in the garden of forking data, there are 4 possible paths drawn here on the screen. And then we considered the second possibility, the second draw from the bag. We get another marble, and there are 4 possibilities for that as well, the same 4 possibilities, but those branch off from the previous 4 possibilities because these give us different data sets, different samples, depending upon what happened in the past and what happens on the second possibility. So there were 4 possibilities on the first draw, and there are 4 plus 4 plus 4 plus 4, or 16 possibilities on the second draw. So 16 possible different data sets at this point. And then the third and final draw in this example, the third possible draw from the bag. Again, whatever happened on the first and second draw to give us each of those 16 data sets, possible data sets, each of those has 4 additional paths drawn from it, the same 4, 1 blue and 3 white marbles, and for a total of 64 different possible data sets in 3 draws from the bag. Okay, why have we done this? We're doing this because now we have a device, a visual device, that lets us count up all the ways that any particular data set could arise, assuming the contents of the bag are 1 blue marble and 3 white marbles. And again, we're going to look at the other possibilities next, but we're going to stick with this one for now. So let's trace that out. Let's imagine our first observation, and that's a blue marble at the bottom of this slide. And there's exactly 1 path by which that can happen, highlighted here in red. So there's 1 way for that first observation to happen, assuming or conditioning on that the true contents of the bag are 1 blue and 3 white marbles. And now the second observation is a white marble, shown at the bottom. How many ways could that happen? There are 3, branching off from the first possibility. All the possibilities on the right-hand side of this garden of forking data have already been foreclosed, have already been forbidden by the fact that the first observation was blue. So the second one is white, and there are 3 paths now by which this data set could arise. And then we consider the third and final observation. This is blue. And so we trace the blue paths that originate from the 3 valid paths that we had so far. So there are 3 total ways for the sample to arise, assuming the bag contains 1 blue and 3 white marbles. So let's summarize that, because this is our goal actually in Bayesian inference, is to get this information, to count up the number of ways to see the sample if the bag contains, in this case, 1 blue and 3 white marbles. Or more abstractly, we want to count up all the ways the data could arise, assuming for each explanation, assuming some explanation were true, just playfully for the moment, we count up all the ways that the data could arise given that explanation, and then we're going to compare the different explanations based upon these counts, and that is Bayesian inference, although it's usually presented in a fancier way. So let's put that into our table of results now. We come back to our table from the earlier slide, summarize the garden of forking data. In the second explanation, there's 1 blue and 3 white marbles. There are 3 ways to realize the sample we have with that. Let's consider the other possibilities now. We get the first one pretty much for free. It's forbidden by logic. The bag cannot possibly contain all white marbles because we have seen a blue marble. We have seen 2 of them, in fact. Well, they could be the same blue marble. Likewise, the 5th explanation, all blue marbles, is also forbidden by logic because we have seen a white marble. But what about the other 2? Possibility 3 and possibility 4 with 2 and 3 blue marbles respectively. Let's take those in turn. So consider the third explanation, 2 blue marbles, 2 white marbles. Let's draw the garden. 2 blue marbles at the bottom, 2 white marbles, and then from each of those branching off again, 2 blue, 2 white, and now we trace out all the ways the sample could happen. So from the bottom, we sample a blue. There's 2 ways for that to happen. From each of those, we sample a white. There are 2 ways each for that to happen, so now 4 in the middle row of the garden. And then for each of those, we draw a blue marble, and there are 2 ways for that to happen again, and so we end up with 8 possible paths. I'll give you a moment to trace this with your eyes and count it out. You see that there are 8 valid paths consistent with the sample of blue, white, blue. Now the 4th possibility, 3 blue marbles and 1 white marble. Same exercise, going to draw the garden and trace the paths. 3 blue marbles, 1 white to start, and then from each of those again, 3 and 1, and then 3 and 1, and now 3 ways to get a blue, 1 way for each of those to get a white, and then 3 ways to get a blue from each of those for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 valid paths, ways to realize the data, assuming the bag contains 3 blue and 1 white. So let's summarize now, put all the numbers in the table. The first explanation is forbidden because if the bag didn't contain any blue marbles, we wouldn't have seen any. So there are 0 ways for that explanation number 1 here, to explain the data. And the second one, this is the one we started with, there are 3 ways, and then 8, and then 9, and then again 5, forbidden by logic because we have seen a white marble. So these are relative numbers. These are numbers of ways for each explanation to produce the data we've seen. And this is basically it in Bayesian inference. Real data analysis problems, well, this is a real data analysis problems. The typical, let's say typical data analysis problems in the sciences and in basic research look a lot fancier than this, and these calculations are often automated for you, but this is the logic of probability theory here, is we count up all the ways the data can occur, and then we use across a range of explanations, and then we use those counts to compare the plausibility of the different explanations. So let's try to summarize that now. Let's make this feel a little bit more like probability theory. It's what I call the unglamorous basis of applied probability, things that can happen more ways are more plausible. And that's pretty much it. Why do we do this? Because it's unreasonably effective. That's why. And it's nothing more than logic. We state our assumptions. Those assumptions have implications for the data, for the observations. And then if assumptions that are more compatible with observations are considered more plausible. So summarizing at the bottom, we have all the possible compositions of the bag. These are explanations for the observations emerging from the bag. Each of those we could assign some index, what we call a parameter here, P, which is just a proportion of blue marbles in the bag. This is not necessary, but this is the more conventional way we talk about these, and this will help us relate it to the coverage of water on the Earth example, which we're going to return to shortly. So the proportion of the bag that contains the proportion of the bag that is blue marbles ranges from 0 to 1, and the possible explanations are 0, 0.25, 0.5, 0.75, or 1. For each of those possible explanations, we deduced that there are 0, 3, 8, 9, 0 ways, respectively, for each of those explanations to explain the data. And then finally, these ways are meaningful only to the extent that they are different, relatively different from one another. The absolute counts are not what is important. All of them could be small, all of them could be large. What matters are their relative values. And so what we do to deal with differences in the sizes of data sets and the arbitrary combinatorics of particular problems is we normalize these counts so that they all sum to 1. And that's all I've done here is taken the sum of the ways to produce data column, the 3 plus 8 plus 9, and divided each of those numbers by that. Here I can show you in code what that means. We just make a vector in R called ways, which contains the numbers 3, 8, and 9, and then I divide that by the sum of the vector, and that gives us the number shown on the right-hand column of the table, the plausibility column. These are 0.15, 0.4, 0.45. These are probabilities. I'm calling them plausibilities because that's their function in inference, but this is all probabilities are as well. So the code snippets I'm going to show in the lectures are all R code, but as I'll remind you a little bit later in this lecture, almost all the code examples in the book and the course have been translated to other major languages like Python and Julia. So if you look at the course webpage, you can plug into your preferred scripting environment. Okay, this procedure can handle the data all at once or as it comes in, and that's a great feature of Bayesian inference. There's this thing called Bayesian updating. That is, when new data arrives, we don't have to redo the whole calculation. We can just take the old answer and update. So let me show you the logic of that. And actually, surreptitiously here, we're deriving a law of probability, the product law. So we get one more draw from the bag, the blue marble. Remember our 5 conjectures, our 5 possible explanations for the contents of the bag. For this new sample that we've just seen, a blue marble, it's very easy to count up the number of ways each of these conjectures could explain it. If the bag is all white marbles, there will be 0. If there's one blue marble, it'll be 1. And if there's 2, there's 2. If there's 3, there's 3. If there's 4, there's 4, right? Hopefully that's obvious. And then we have our previous counts, 0, 3, 8, and 9 from the sample of 3 that we had before. Instead of redrawing the whole garden and doing this over again, we can just multiply these numbers together actually. Why? Because remember in the garden, at each additional step, each additional ring in the garden that grew, you were multiplying the number of steps. It went from 4 to 8 to 64 as you branched out. And that was because they were multiplying. So if events happen independent in this, the proper way to count all the possibilities is just to multiply the counts together, right? So think about it this way. If there's 2 ways for one thing to happen and 2 ways for some independent thing to happen, then there are 2 times 2 or 4 ways for both events to happen together. And that's all we're doing. So we multiply. Obviously 0 times 0 is still 0. 3 times 1 is 3, 8 times 2 is 16, 9 times 3 is 27, and 0 times 4 is 0. So now our counts are 3, 16, and 27. The 3 blue marbles is looking more and more plausible here, more and more likely, but again, it's the relative values here, the relative numbers of ways that matter, not their absolute counts. In any reasonably sized data set, if you did this manual kind of counting, the numbers would get really astronomical, really very fast because of the way combinatorics work. And so that's another reason we must normalize at each step by summing and dividing each by the sum. Okay, let me try to do some summary here. What are the rules in Bayesian updating? What you must do is state some causal model, some mechanistic model for how the observations arise, given each possible explanation. Now, we don't know the true explanation, but you have to know enough about or believe enough about the mechanisms of each explanation that you can state what the data sets that would emerge from it look like. Second, you count the ways the data could arise for each explanation using the assumptions you made in step 1. And then 3, relative plausibility is the relative value from 2. And what do we do with these relative plausibilities? Well, lots of things. They're used for inference, and we'll see lots of examples of that going forward. But you'll see as we turn back to the water on the Earth example, you'll get a sense of what it does, what the information contained in these relative plausibilities. But they tell us, in a crude sense, which explanations are plausible and which ones are much more or much less plausible than others. Okay, so let's go back to the globe now, and we're going to repeat all that counting, but now for an infinite number of possible explanations. Why infinite? Because there are an infinite number of proportions between 0 and 1, and we want to rank them all, or nearly all of them. So for each possible proportion of water, we're going to count the number of ways the data could happen. And this requires us, as always, to state how the observations are generated. And that's how are they generated? Well, by tossing the globe around, not by throwing meteors at the Earth and counting splashes, right? So let's imagine that. Let's imagine here I've virtualized the globe tossing exercise in the computer, and we're going to take a first toss from the virtual globe, and that'll happen on the left here, and on the right I'm going to draw a graph of the relative plausibilities of each proportion. So if you look at the graph on the right, the horizontal axis is all the possible proportions of water from 0 to 1. It's the proportion of water on the globe. And the vertical axis is this thing called density, which I'll explain in a moment. And the dashed line that you see at 1, this is the information we have before we see any data. We'll talk more about that in a moment. So we start and we get a first sample, and it's land. And the implications of that, according to counting all the ways, is this diagonal line. Starting at its maximum on the far left at 0 proportion of water and going down to 1. So I'm going to pause for a second and talk a lot about this one particular slide, and I'll move more quickly through the slides that follow because they have the same structure, but we need to get this right to begin now. So this dashed line that I mentioned before is typically called the prior. That was what we knew about the relative plausibilities of each possible explanation before the data arrived. And this red or pinkish diagonal line is called the posterior, and that is the relative plausibilities of each possible explanation after the data arrive. And the observation in this case is just one land sample, right? So why does the posterior have this shape? Well, I'm going to talk about this on multiple slides to come, but I'll say it now too. It's just the relative numbers of ways to observe a land sample given each possible portion of water. So think about it for a second. So on the far left, if the Earth had no water on it at all, the value on the horizontal axis was 0, then that would be the maximum number of ways, that is all the ways to observe land. You would always observe land. And then as the proportion of water increases as we move to the right on the graph, the relative number of ways to observe land decreases, and it decreases in a linear fashion because that's how proportions work. Until you reach 1 on the far right, and then it would be impossible to observe land. And so that is where it reaches 0, because there are 0 ways to observe land if the proportion of water on the Earth is 1. And so it has gone to 0 at that point. So there is nothing about the shape of this posterior distribution here that is anything but logical. It emerges purely logically from our assumptions. There is no choice about it after the description of how the globe tossing exercise works. Everything else is deduction from that point on. Okay, final thing to say about this slide is density, this weird word density. Uh, Density is a particular concept in probability theory, and we're going to talk about it multiple times in the course. For now, it's sufficient to understand it as relative plausibility of the proportion of water and its relative value. And the actual numbers, don't focus too much on them right now. We're going to talk about this more in the weeks to come, because sometimes it does matter. But for now, it's fine to have a heuristic understanding of this as relative plausibility. Okay, now let's take a second toss from the globe. So I'll repeat the first one, and now a second one, and we get water. And now here's the updated posterior distribution. And I've left the prior distribution from the previous sample, that is just one land, on there for comparison, so you can see in each step of the animation what has changed by adding one more data point, as it were. So let's focus on this shape, this little dome, for a second, and ask why it needs to look like this. It has to look like this because of, well, logic, because Bayesian inference is just logic. But it's no accident that it looks exactly like this. So it just comes from multiplying two diagonal lines together. So let's start in this slide on the far left here and look at these. There's a pink line and a blue line. The pink line is the relative plausibility of a single land sample for each possible proportion of water. That's the graph on the far left. The relative plausibility of land across all the proportions of water on the horizontal. And then in the middle of this slide, we have the same construct, but for a water observation, a single water observation. It's still linear, but it's just flipped, because now we're talking about the other possible event along the proportion of water on the globe. That is, it's maximized at 1, and it's 0 at proportion of water of 0. And remember, in the garden of forking data, when you get independent observations and you want to update, you multiply the plausibilities, or the numbers of ways, together. And so we can literally multiply these two curves together, and that's how we do it. What does that mean? That means for each possible proportion of water on the horizontal axis, here I've drawn these vertical dashed lines to give you a visual guide to what I'm going to say. We find those matching values and we multiply them together, and then we put the product, the result, on the graph on the far right, and this is our new posterior distribution. So you can imagine starting on the far left and tracing out that multiplication, and it will increase until the midpoint, and at the midpoint it's maximized because there's no low values. Both lines are at the same value here, and there's no implausible observations to drag the whole curve down, but this must be symmetric because the lines are symmetric, and so as we continue on to the right, it goes back down to 0. Why? Because at a proportion of water 1, it would be impossible to observe land, and so that cancels the curve, essentially. I hope this makes some sense. I'm going to stick with this logic for a little bit longer. What I want you to get from this is that the shape of these curves comes entirely from the implications of how the proportion of water relates to the probability of seeing a land or a water. That is, those diagonal lines are mechanistic assumptions about how the sampling works, and then all Bayesian updating is multiplying a series of these diagonal lines together to get some curve. But the number of possible curves that can arise from that is really huge, depending upon the exact sample you get. So let's move towards that and give you some appreciation for it. Oh, a little bit of drawing the owl, if you don't mind. If you want to mechanistically play with this, just convince yourself in R, this one line at the top, plot 0 to 10 times 10 to 0, will give you the shape, the exact shape of that posterior distribution seen here. Okay, now we get a third toss from the globe. So again, here's the first one, and the second, and the third, another land. And so now we've got land, water, land, and we've got this particular curve, which does not maybe look to your intuition like it merely emerges from multiplying diagonal lines together, but it does. It comes from multiplying these three diagonal lines, the land, water, land line. So it shifted more towards land to the left half of the graph because we have twice as much evidence for land as we do for water at this moment. But notice that basically all the proportions of water are still in play because we have so very little data. And now you can start to appreciate how relative plausibility works. As we get more and more evidence, this curve is going to get more and more concentrated in a particular region of the horizontal axis, and that's how the inference works, and we get more confidence. So again, a little bit of drawing the owl. If here's one line of our code that will draw a plot which has the same shape, exact shape as this posterior distribution. You're just multiplying these vectors together, 10 to 0 and then 0 to 10 for a water observation, and then another 10 to 0 for land. And those are those diagonal lines. Okay, now let's do 10 samples. And I'm just going to animate the whole thing through here so you can get an idea how this works. And you can back up the video a bit and watch this over and over again if you like, and develop some intuition for what's going on. I think you'll see all these principles are applied, and each time we get another sample, we just multiply another diagonal line, whether it's for land or for water, and that adjusts the curve. So you'll see when it's a water sample, the curve shifts to the right, like there, and when it's a land sample, it'll shift to the left. If we get it, yeah, there we go, land sample, and then back again. Notice that the curve is also getting narrower and taller, and that's because the total plausibility is fixed in this distribution, because the distribution always sums to 1. It sums to 1 because we make it do that. That's that normalization step. And so the area under the curve is fixed to be 1. That's what makes it a probability distribution. And so as it gets more concentrated, it has to get taller. Otherwise, its volume wouldn't be the same. Or not its volume, its area, right? The area under the curve. So this is the sense in which more and more evidence leads to a smaller range of values on the horizontal axis being plausible, and you have greater and greater confidence. That's a nasty word I don't like to use. That more and more plausibility is bunched up on a smaller number of values. Okay, so let's think about this a little bit more animated. We start out with this sort of no information state, shown in the upper left here, of having no idea at all how much water is covered, how much of the Earth is covered by water. After one sample, we get this diagonal line. Then we sample a water, and now there's essentially 2 of these diagonal lines put together, and it's symmetric evidence. And after a third, and after a fourth, and after a fifth, and after a sixth, and after a seventh, and after an eighth. And what I want you to realize about this whole procedure is that we've done it step by step, one sample at a time. But of course, you could take the whole sample and do it simultaneously as one big updating moment. Go straight from the flat prior in the upper left to the curve in the lower right if you just gave the machine all the data at once. And that's how we usually do data analysis. But you can do it step by step. Like this, and that's why it's called Bayesian updating, because there's an implied series of updates as the golem, the little machine, has learned things. It thinks it's learned things from the data using the assumptions you've programmed it with. So this is sort of the world's most basic example of Bayesian inference, but it has all the general features. So I want to spend a few slides now just talking about those general features, and they may be in conflict with your previous statistics education, and that's why I want to call some things out. So the first thing to notice is there's no minimum sample size in this business. There's no such thing. 1 data point's enough. In fact, 0 data points is a sufficient sample size to do analysis, and we'll do a lot of analysis in this course with 0 data, because that's how we understand what the model thinks before it sees any data at all. That's how we explore the implications of the model before we add evidence. That's something we'll call prior predictive simulation. I'll show you an example near the end of this lecture. But usually we want some data. If you have 1 data point, it's already worth updating, possibly. And of course, as you see here, like the example on the slide, you don't learn a lot from 1 sample because most explanations are still in play. So your beliefs don't change a lot. But there's no sense in which there's some minimal sample size required for inference. The relative plausibilities tell you here that very little can be concluded. You haven't learned much. Second, the whole shape of the posterior distribution, the blue curve on this slide, it essentially embodies the sample size. So in other statistical frameworks, sample size, it has some kind of magical quality. You're always reporting it and talking about it, and you need to use it to calculate things called degrees of freedom and so on. Sample size has no comparable role in Bayesian analysis because all the information that is relevant to inference about the explanations has already gone into constructing this curve. And so if you get new data, or for anything you'd like to know about the explanations, is already embodied in the curve. And if you get new data, you don't need to redo those calculations. You can just start with the curve you have and go forward doing updates. Um, uh, One thing will help you get an intuition, though, is of course sample size matters. And as you get more and more data, the curve gets narrower and taller. Third, point estimates don't really have a big role in Bayesian inference because the estimate is the curve. What do I mean by this? So given any particular posterior distribution, like the dashed gray one on this slide, you can pick a lot of reference points. So you could take the point at where it's maximized, for example, the mode, and say that that's your best estimate, if you like. You could also take the mean. And which of these is the best summary of the curve depends actually upon a lot of sort of extra scientific criteria, like the costs and benefits of different actions that you take using this information. And those are not usually criteria that we have strong feelings about in basic research, but you may very well in industry. And if you want to read more about this, in chapter 3 of the book, I talk about how utility functions, that is explicit assumptions about costs and benefits, can be used to decide which point estimate you might want to use. But in general, in scientific publications, there is no valid point estimate. The distribution is the estimate, and we want to report the whole distribution to a useful level of accuracy. And when you do anything with the model, as you'll see again and again in this course, like produce predictions or report causal effects, compute counterfactuals, anything at all, you always use the entire distribution. There is no case in which you take a summary of the posterior and then do subsequent calculations with it. Or as I like to say, summary is always the last step. All calculations and machinations with a Bayesian model must use the entire posterior distribution all the time. Otherwise, you're throwing away uncertainty and you'll get overconfident answers. Okay, fourth thing I want to say is intervals also don't have a really strong role to play in Bayesian inference. I summarize this at the top of this slide by saying there is no one true interval, but you can report any interval you want. All they're doing is communicating the shape of the posterior distribution. So there's an infinite number of intervals that you could draw, and they're all arbitrary. They just have different utility given the communication function you have in mind. So you could draw a 50% interval, for example. This interval I've drawn here is the middle 50%. Middle 50% of the quantiles of the probability mass. So it captures a central range, but there's actually an infinite number of 50% intervals because you could slide this interval left and right and still capture 50% of the mass. So the fact that this is central, it's heuristic and it seems reasonable, but there's no strong logical reason that you would have to use this at all. And the same is true for any other width of interval. We could make something bigger, like 89%. I'm quite fond of 89% intervals. I use them in the book, I use them in the course, and I use them in my papers. But again, it's just an arbitrary number. It covers a very wide range of the most plausible values, and it's a convenient summary sometimes, but there's nothing special about it. There's nothing special about it because nothing special happens at the boundary. At the edges of these intervals, it's just a continuous reduction in plausibility as you leave the interval. There's no special cliff that anything really falls off of, even though it looks like there's a cliff at the end of the interval. We could use really wide intervals. Sometimes this is the right thing to do because you want to make some argument about really all of the plausibility is in some range, and so you can use 99% or even 99.9% intervals to report that range. Conventional 95% intervals that you see quite often in scientific publications, this is an obvious superstition. And what do I mean by that? People sometimes endow the 95% interval with seemingly magical powers, as if this was the only interval you needed to report, and if some particular value like 0 is contained in that interval, then that means there's no effect. And none of this is logical. It's purely conventional, but people know that. If you push anybody a little bit, they'll admit, yeah, of course it's a convention. But we're humans and we live kind of in a prison of conventions, right? That's the way culture works. So it's hard to break free from these things. But I think we can break some of that spell by just stating publicly, look, this is a superstition. There's nothing logical or mathematical about some particular 95% interval. And this is especially true in Bayes because we're not using these intervals to do error control. That's not what we do with them. There's nothing about type 1 error here or so on. That now I want to say that it doesn't mean Bayes doesn't do error control. Of course it does, because it finds the most plausible values and helps you avoid mistakes. But the intervals don't have that function. They're not calibrated to do that. Or I keep saying, nothing magical happens at the boundaries. Yeah. So one last slide before we take a little bit of a break here. We all need a bit of a break. So an installment I want to call Letters from My Reviewers. So like all of you, I write papers and I put stats in there. And one of the questions I often get when I teach is, how do you, when you put Bayes in your papers, how do you deal with reviewers who are ignorant about Bayes and say silly things? And I always say, well, you try to educate them and remember that you're talking to the editor, not to the reviewer. But the comments that reviewers write are often quite overconfident when they're ignorant of Bayes, because they'll project their ignorance onto me because they don't know who I am. I'm just some anthropologist, right? And that's fair. I mean, I don't want any special treatment from reviewers. But here's one that I collected that I think is quite telling about the kind of latent assumptions that come from other statistical frameworks. So this one reviewer said, this was last year in 2021, the author uses these cute 89% intervals. I'm guilty. But we need to see the 95% intervals so we can tell whether any of the effects are robust. So they were, the reviewer was saying that I needed to add conventional 95% intervals. And the implication here is they were going to see if 0 was contained in any of those intervals, and if so, they would declare the effects not robust. Now, there is no statistical framework in which this program is legitimate, but you see these things in reviews. My response, of course, is that, look, this is Bayes, and we're not doing error control with the intervals. Significance tests here are illegitimate. The width of the intervals is irrelevant, and all of the prediction curves and everything else contained in the paper uses the entire distribution, not just what's contained in the intervals. The intervals are just there for a short summary table. That's all they're for. Yeah. So keep that in mind when you deal with these things. An arbitrary interval contains an arbitrary value, and that's not meaningful. We use the whole distribution for all calculations, for predictions and everything else. Okay, at that point, I think let's take a little pause or pausa. And at this point, if you want to review the slides that have come so far and mark down things you didn't understand or review, that's a good use of the time. And then from here, we're going to finish up this lecture by applying basic Bayesian updating, the result we get from basic Bayesian updating to some new stuff. Okay, welcome back. Before we jump back into it, I want to remind you that while the examples I'm going to show assume you're using R, I have no special affinity for R really. It's just that in my professional community, most people use R, and so that's how I teach the course. But the course and the book have been translated into other languages, and if you go to the course webpage, you'll find links to those materials. So there's no reason to suffer under R if you don't want to. Okay, what I want to do in the second half of this lecture is deal with the formalities of this now. So the examples I gave you so far, the bag of marbles, the globe tossing problem, those are very cartoon problems, and I haven't really showed you how the calculations work. And I promised I would help you draw the owl in the first lecture. So let's do some drawing of owls now. And there are multiple parts to this, to drawing the owl in this context. And the first is learning how to write down the assumptions of the explanations. And what this means is writing down models, data generating models, in a kind of universal notation that we'll use again and again in the course, and that you'll see in standard scientific reporting as well. Um, and this form of notation communicates all of the probability assumptions of the model, and then you can use that to do the calculations from there. And then that's the second step, is you actually have to know how to do the code, in a sense. And so far we're just counting, and that's what we'll keep doing. We'll just counting. Okay, so let's deal with the formalities first. How do we do the notation in this case? We're going to keep going with the globe tossing problem. In the globe tossing problem, there are two kinds of variables. There are data and there's a parameter. Let's think about the data first. The data are the things we observe. The observed variables are called data, and I'm going to denote these as capital W and capital L. Capital W is the count of the number of water samples we've gotten, and capital L is the count of the number of land samples. What we want is an expression for the number of ways to realize these two numbers, W and L, given some explanation, little p, where little p is the proportion of water on the globe. Now, the exact letters I'm using here are not important. I try to stick with conventions, and proportions are usually denoted with a p, and so that's what I'm using. But you can use whatever letter makes you happy. Okay, so it turns out that we don't have to do the Garden of Forking data thing manually. There's a well-known formula in probability theory, the binomial sampling formula, which gives us the number of paths through the Garden of Forking data for this particular problem. That is, given some proportion of water P, this is like number of blue marbles in the bag for a very, very large bag that contains like 10,000 marbles. The number of ways to see W and L, where W is the number of water and L is the number of land, is this expression on the top part of the slide here. And this is the binomial sampling distribution, the thing with the exclamation points, the factorials in it. And the details of this are not so important. I just want you to understand that it's just a mathematical expression for the number of ways. That's all it is. And in all statistical programming languages, this function is built in. You don't have to know it. In R, it's called dbinom, the binomial density, and showing you some code at the bottom for how to get the answer for 6 water out of 9 total tosses, assuming that the globe is covered in 70% of water. And then you get this number, which is a probability, which is the relative number of ways that 6 out of 9 could happen, assuming 0.7. For that to be meaningful, you have to consider other values other than 0.7, right? And that's how we get a posterior distribution. We also need a prior for P, that is an initial state of information. And in this case, the right way to do this for the example I showed, that is that horizontal line of sort of maximum ignorance, not knowing anything about which is more plausible than any other, is we just assign a constant. And in principle, it doesn't matter which constant you assign, because everything gets normalized later. But this is a uniform distribution, and the way the uniform distribution works is, in this case, that the constant is 1, because that means the area under the curve will be 1. But that's not the important lesson. The important lesson is that this gives us the relative plausibility of each possible P before we see the data. And now we're going to update. So just repeating the probability assumptions at the top. I'll say again what they are. The formula in the top left is the binomial sampling density. This gives us the relative number of ways to see the sample, conditional on the explanation. And then in the upper right, we've got the relative plausibility of each explanation. And now the posterior distribution, when we update, is just a normalized product of these two things. And what that means is, for each possible value of P, to get the plausibility or probability of that P conditional on W and L, that's what the PRP vertical bar WL near the bottom of the slide means. We multiply the things at the top together, and then we normalize. And so there's a big section in the book, in chapter 2 of the book, about this if you want to learn more and chase down some citations to these things. But just know that all that's going on here is that multiplication that we did when we did the Garden of Forking Paths and we did updating. This is why it's multiplying. We multiply because that's how the garden counts, as I say at the bottom of the slide. And then that probability of W comma L, of W and L, that's the normalization constant. And it's just in probability theory, that's the way we write that normalization constant as the unconditional probability of the data. Okay, that's all nice, and that's just notation, though. We haven't actually calculated anything yet. So you really want to draw the owl. If you want answers, you've got to do some calculations. So let's do that. Let's do this with numbers now. Leave the mathematics aside and do some real coding, and this is where the action really is. So for each possible value of p, we're going to write some code that will compute the product of the probability of W and L conditional on that p times the probability of that p, that is its prior probability, and then we're going to normalize those things so that the relative sizes of the products from the second step are the posterior probabilities. So let's see how it's done. Do it graphically, and then we'll look at some code. So we're looking at a very coarse grain version of a posterior distribution for the globe tossing example. Now, on the horizontal axis, again, we have the proportion of water from a completely dry planet on the left to a completely wet planet on the right, and I'm considering only 3 possible explanations of the data. The 3 points that I've drawn here. The first is 0, the second is 0.5, and the third is 1. And I've ranked them by their relative plausibilities just by doing the multiplications described in the previous slide. And you'll see that the only one still standing is 0.5 because we observe some land and some water. As we increase the number of points we consider, so now here's 5 values, you'll see we get some other possible explanations as well. So now 0.25 and 0.75 are in the game, and those are not illogical. They're still possible. Neither is as plausible as 0.5. However, we can increase it even more to 10, and you'll start to see that the posterior distribution takes shape. And this procedure that we're going through here is a really simple way to do Bayesian inference, completely legitimate. We don't consider technically an infinite number of explanations, but a very large number at whatever density of the grid that we're interested in. So for example, here at 20, again on the left of this slide, you can see that now we've got the recognizable shape of the posterior distribution from before. And at 1,000 values, that's probably the highest accuracy that you're going to care about. And anyway, and you get the curve you'd get from doing the integral calculus, but doing it numerically without having to bother with those things. So this technique is called grid approximation. I say a lot about it in the book as well. We're not going to use it a lot in this course, but I use it now because it's an easy way to get engaged and see exactly what the logic is, because this is all there is to Bayesian updating. And this will be subsumed behind a more convenient interface later on. So it's nice to understand what's going on now. So I want to walk through the code in chapter 3 where this is explained, where grid approximation is used, so that you have another chance to understand exactly what's going on here. So I've just repeated the code from the previous slide here. And we're going to take each of these lines in turn and show what the implication is. The first thing we do is we set up the grid. The grid is the list of possible explanations we're going to consider. And so all I've done is generate a sequence of numbers from 0 to 1, 1,000 of them evenly spaced. And I plot these on the left. This is our first bird sketch. And now we set up the prior probability, the probability of each value of p. And in this case, I've just repeated the number 1 1,000 times because that's the uniform prior distribution that I talked about before. And you can see this plotted on the lower left. Now we want the probability of the data. That's the probability of the W and L samples. And this comes from the binomial sampling formula. So we use the third line of code to get that, and it gives us this curve, which you'll recognize because in this example, the shape of the posterior comes entirely from the data. And then finally, we normalize that in the last line, or rather, in the last two lines, we get the posterior distribution by multiplying the probability of the data by the probability of the parameter p, the explanations, and then we normalize in the last line, and we get the last example, which has the same shape as the third curve, but you'll notice that the vertical axis has different units because it's now a probability distribution. You can play with this code, and I encourage you to do so. Change different assumptions in it to get an idea about how these things respond. This is how you learn. Develop some intuition for this. It's quite typical when you're learning this stuff that you'll be good at the calculations before you really understand why you're doing them. That's perfectly normal. That's how most psychologically healthy people learn complicated skills. They can actually do it well before they can really explain it. And you develop a verbal understanding of things by playing with multiple examples and developing generalized knowledge that applies across cases. And so playing with the code and breaking stuff, don't be afraid to break it, is perfectly good so that you can see how the posterior distribution changes. So let me show you one example of that just now before we move on. Let's change the prior. So first line's the same grid as before, 1,000 values between 0 and 1. And now I'm going to create a prior that has some more scientifically interesting implications. This is a prior, you can see it in the lower left, that considers wetter worlds to be more plausible. The idea that, well, from space the Earth looks pretty blue and it's got a lot of clouds. Obviously there's a lot of water there, so higher values are more plausible than lower values. But notice that it's wrong in the sense that it's maximized at the far right. That is a totally wet world, and the data is going to have to wash that out, but it'll have no problem doing so. And then the probability of the data curve is exactly the same as before because the data have not changed. Although when you play with this code, I encourage you to change the data and see what happens. And then finally, we get a new posterior distribution, and I've imposed it over the previous one. The previous one is in gray, and here's the new one in black, and it's shifted to the right a little bit because of the prior. That's the action of the prior here. And if you want to take this code and play with it, you can make the prior increasingly extreme to see how strong it needs to be to really strongly influence the posterior, and that's how you develop intuitions for these things. Okay. In practice, we're not going to do a lot of grid approximation in the course. But I said it's a good conceptual way to bootstrap yourself up to understanding what's going on. In practice, we're going to be using other methods like something called quadratic approximation, which I'll explain in the next lecture. And then starting around the middle of the course, we're going to start using Markov chain Monte Carlo, which is the main workhorse. It's actually a family of methods for sampling from posterior distributions, and you can fit quite complicated models using it. Okay, so we've got a posterior distribution. What are we going to do with it now, right? Just look at it, put it up on the mantle, invite our neighbors over to look at it. No, we want to do something with it. We had this model and we educated it with data, and now we want to ask questions of it. And one way to think about this is you've tutored the golem, and now the golem can say what the world it's learned about is like. So it can make predictions, it can generate counterfactuals. You can do lots of different kinds of calculations with models. They're not inert, they have behavior. And in really simple models, it's true that you can just look at the parameters, in this case p, the proportion, and that's the answer you're after. But in even reasonably complicated models, there are a large number of parameters, a dozen, 2 dozen, sometimes thousands, and it's not possible to just gaze at tables of parameters and understand how the model behaves, because the model's behavior is a function of all of the parameters at the same time. And I'll say this many times in this course, I'll say it again now. A model's behavior is a function of all of its parameters simultaneously, and there can be many, many parameters, and they interact in non-additive ways. So you need to get used to using the posterior distribution to calculate things afterwards. That is, things like predictions, and that's what we'll focus here. We're going to go from the posterior distribution to what the model thinks additional samples would look like. This is one of the more direct implications of an updated model. When we do this, we have to use the whole distribution. We're not going to take a point from the posterior, like the point where it's maximized, but we're going to use the whole distribution. You could do this mathematically, that is, averaging over a probability distribution uses an integral from integral calculus. And basically, 95% of the integrals in statistics are just there to do an average of some kind. Averages over continuous spaces use integrals. Sometimes those integrals cannot be done, or maybe you're not comfortable with integral calculus. So in this course, the way I do it is we just take samples from the posterior and we use those samples as a data summary exercise to do calculus without realizing it. So let me show you what I mean. So on the left-hand side of this slide, what I'm showing you are random samples from the posterior distribution. This is our proportion of water posterior, and then the pink lines are random samples from it. The more plausible values are sampled more often, so the bouncing line stays near the middle more often, but you can sample any value on this line except for 0 and 1. When we take any particular sample from this posterior distribution, it implies a distribution of observable data. So now in the middle of this slide, what I'm showing you are for each of the bouncing lines on the left, we've got a histogram of black lines in the middle, which are if we took 9 additional samples from the globe, what's the probability of each number on the horizontal axis, each number of water samples between 0 and 9. So let's say this again. If we take 9 additional samples from the globe, we could get anywhere between 0 and 9 water samples out of the 9. And the black lines in the middle are the histogram of the possibility of each of those outcomes, assuming the particular location of the pink line on the left, that is some true value sampled from the posterior distribution. And then the pink line in the middle graph is a sample from that. That is, we've realized some particular sequence of 9 and gotten some number of water samples. And then we're going to add that to a growing histogram on the far right, which is something we call the posterior predictive. And so as we take a sample on the far left, we get a histogram in the middle, and we take a pink sample from it, and then we add that to the distribution on the far right, and that's what the pink line on the far right, you'll notice it increments. Every time the pink line on the far right lands on something, that line gets a little bit taller. You can see it? Yeah? I'll pause for a moment so you can watch it. So what we're ending up with on the far right is a distribution of possible observations, of predictions, that is averaged over the whole posterior distribution because it is comprised of samples from the whole posterior distribution. So even though any particular value of P, of the proportion of water on the globe, implies a unique distribution of predictions, which is shown in the middle of this animation, when we use the whole posterior distribution, we will average over a bunch of those possible distributions of predictions. And that's what we want, because that's the only way to honestly report all the uncertainty in the posterior distribution. And that's what the thing is on the right, the so-called posterior predictive distribution. And that's our goal for predictions from Bayesian models, is always the posterior predictive. Well, I shouldn't say always. It's always the first step. There's other things we might do, or other things we might do first. But in models like this, this is the way to do predictions. You never take a single point from the posterior and give predictions for that point. That throws away a lot of your uncertainty, and you get overconfident answers. Okay, let's run that fast forward now so you can think about it again, and I'll repeat some of that because I know this is maybe a little bit weird. Anytime we do calculations with Bayesian models, we take the posterior distribution shown here on the left, we sample values from it, and then for each of those sampled values we do additional calculations, and then we collect all those calculations together, and then we have a new distribution. A distribution of calculated answers, and in this case it's a distribution of predictions shown on the far right, and that distribution of collected predictions will naturally be averaged over all of the uncertainty in the posterior distribution, so you can see how it accumulates. And you'll notice that the posterior predictive is a lot flatter and more spread out than the distributions in the middle of this animation. The middle are the predictive distributions for single values of P, and those are narrower and more confident. Okay, To draw the owl and do this for yourself, there's a big section in chapter 3 of the book that walks you through this as well. Box 3.2 here is the same code that I showed you before when we drew the owl, just to compute the posterior distribution using grid approximation. To take samples from this so that we can compute the posterior predictive distribution, you just need one line of code, and show it to you here. You can use the sample function. You sample from the grid. That's why it's sample p grid. Remember, grid is just the list of all the possible explanations of the data. And prob equals posterior means we sample them in proportion to their posterior probabilities. We're going to sample 10,000 of them. That's what 1E4 means. And we're going to do it with replacement. And then after you run that line, the symbol samples contains 10,000 probabilities sampled from the posterior distribution, and they appear in proportion to their posterior probability. So let me show you what that looks like if you plotted out the contents of samples. If you just plot samples, you get the graph in the lower left here. It's just a big smear, but you notice it's like you're looking down on a hill of the posterior distribution. And then looking at this hill from the side as a density on the right, that's the posterior distribution we started with. Okay, so far we haven't done anything useful. We've just taken samples from a curve we already knew. What's useful now is that it's trivially easy to compute the posterior predictions with one additional line. So this whole animated graph, now with R code 3.26, we just take random binomial samples. We're going to collect them in a vector called W. W is going to be a vector of random binomial samples, 10,000 of them. Size equals 9 means 9 tosses of the globe. And the probabilities on each of those tosses comes from the samples. And so there's 10,000 different probabilities, and each of them is used once. This is the way R code works. It's all vectorized. Samples is a vector, and so of length 10,000, and so W will also be a vector of length 10,000. And this is how the posterior predictive, shown at the bottom of this on the far right, can be computed. And you should try this out, change the posterior distribution, try it again, get a feel for it. And we'll be doing this over and over again in the course, although it'll get more compact over time. It's good right now to really draw the owl, though, I think. Okay, let me try to summarize a little bit of this, because we're nearing the end of the lecture, and I want you to feel like you learned something. So sampling is a way to take hard problems in calculus and make them into easy problems in data summary, and that's why I teach the course using the sampling approach. Most of the problems in the early part of the course could be done entirely mathematically, and if you took a math stats course, that's the way you do them. There is value in that if you want to have a career in math stats, but I can teach a much bigger audience and get them to a point where they can learn the math stats later by starting with this data-oriented approach, where we turn samples from posterior distributions into data and then do calculations on them to calculate all the useful things about models that we need. Later on in the course, we're going to use Markov chain Monte Carlo, and Markov chain Monte Carlo only produces samples anyway. So you need these skills to use Markov chain Monte Carlo, and most applied Bayesian work is going to use Markov chain Monte Carlo realistically. So you need to learn this. So you're learning it now. When you don't need to, it'll merely be a convenience, but after the midpoint of the course, it'll be essential, and you'll already have mastered it by then. Sampling is also incredibly useful because it empowers the researcher to calculate things they'd otherwise need a captive mathematician to do. You can compute all kinds of things with samples from the posterior distribution and knowledge of the data generating model, like model-based forecasts, causal effects, or marginal effects, they're called in some fields, counterfactuals, that is, what if something had been different? What does the model think the data would have looked like? And this thing that I call prior predictions, which is used a lot in this course to understand models and design them. So I want to, as a last example, I want to say what that means. Prior predictions are predictive distributions, but not for the posterior, but for the prior. Remember, priors and posteriors are the same kind of animal. Every posterior distribution used to be a prior distribution, and every prior distribution hopes to become a posterior distribution. So we can repeat this posterior predictive distribution sampling exercise, but now using the prior. Remember the flat line on the left? And when we do that, again, we get for each particular value of p sampled from the flat line, we get a different predictive distribution in the middle. We take a sample from that predictive distribution, and then we pile it up on the right. Now, you're not going to be surprised to see that the prior predictive distribution ends up also being flat in this case, and that's an implication of the prior. But you can do this calculation for much more complicated priors and for models with many parameters where the priors may interact and get a unified representation of what the prior means. So I'm going to say that again. For more complicated models where you'll have a number of parameters and you need to choose a prior for each of them, those priors don't have meaning in isolation. So it's often hard to understand them, and you can always understand them by doing this simulation exercise, by simulating observables from the model. And as a scientist or a researcher, you have a lot of expertise about what you expect the observations to look like. So you know what's scientifically reasonable, and that's the way to understand when priors are reasonable or not. And there'll be many examples. In every example we do in the course, I'll go through this exercise and show you what the prior predictive distribution looks like so that you can understand priors better and that you don't use silly default priors. Okay, let me round out this thing and talk about the overview. So Bayesian data analysis is really as simple as taking each possible explanation of the data, counting all the ways the data can happen, and then considering explanations with more ways to produce the data to be more plausible. Those plausibilities are then useful for lots of things that have implications for observations, and that's why Bayesian data analysis has become so commonplace and mainstream in the sciences and elsewhere. But it really is, this is the basis. It's just probability theory. Or another way to think about this, Bayes is extremely modest because it's just probability theory. It's permissive and flexible, and it gives no guarantees. It puts all the burden on you, the researcher, but I want to encourage you to think that that's good news. The guarantee it does offer is that it's logical. You give it a set of assumptions, and you give it some data, and it will logically report to you which of the assumptions is most consistent with the data. And that's all the probability theory really is in the applications we're using here. As an applied math object, it's a method of logically deducing the implications of data under assumptions that we must choose. The assumptions aren't for free. You have to put some causes in to get some causes out. And I believe that any inference framework that sells you more than this, claims to have more power than this, is hiding some assumptions. That's the only way it could get that power. And those assumptions may not be universally applicable. You may not be comfortable with them. And so you have to be careful. Buyer beware. Yeah. So the Bayesian modesty is a kind of objective honesty in a sense, is that the scientist is in charge, and then the logic can be taken off your hands, which is a huge relief, but there are no guarantees beyond the logic working. Okay. That's not nothing, though. As you'll see in the weeks to come, we're going to do a lot with that logic, and lots of really powerful things can be done with inference this way by taking the load of the logic off of the scientist, because then you can focus on the part that's really interesting and the reasons you got into research, and that is the scientific questions and how statistical modeling can help you answer them. So that was week 1, the first 2 lectures. Next week, we'll look at linear models and causal inference. This is will be a crash course in regression. If you've never had a regression course before, that's fine. I don't assume that you know anything about it. If you want to get a head start on reading, you should read chapter 4. And I'll see you then.